It's a pleasure to be here, and it's already been a very productive time, even though it's been brief. So first I thought a good title for the talk like this is Astronomy in the Cusp, because I think in this decade, transients will be one of the growth areas in astronomy. And that's why I thought the title should be the next big thing, but there are many other next big things, maybe few others. So I thought we should get on to the transient sky, but I can't describe all that I think that will be interesting in this area. So I thought I will describe the Palomar Transient Factory, which on the scale of projects that are being planned is actually a small project, and it's already been very fruitful. Let's see. Okay, so I thought I'd review briefly where sort of my view of where astronomy is, and it's in a fantastic phase. It's extrasolar planets. We've gone from just finding to actually understanding planet formation as a physical process. The process happens with the birth of almost any star, and astronomers are busily working on these details. Surely this will continue in this decade in a big way. Even though I'm not I've never worked in anything to do with the large-scale structure or early universe. As an outsider, I find the progress in that field amazing. It's really amazing to think that through astronomical observations, we can say something about the initial fluctuations, the age of the universe, development of large-scale structure, formation of galaxies, as well as along the way identify matter, parts of the universe that are dominant, such as dark matter and dark energy. I'm sure that continued study of this field will be vigorous and exciting in this decade. Dense matter, this is traditional an astronomical topic because you can't make very dense matter in the lab, at least cold dense matter. And actually there has been a huge progress in this field, but I think some of the astronomical community hasn't paid much attention. About 6 months ago, there was a finding of or a measurement of a neutron star of mass 1.96 plus or minus 0.03 solar masses. This, I think, completely gives us the first empirical or observational evidence that constrains the equation of state of dense matter. I think again, this discovery by Demarest, Scott Ransom, and others, I think shows this field may, in fact, there may be new surprises in this decade. And of course, relativistic astrophysics, in some sense, this has been an old topic and will continue. So if you step back and look at both our accomplishments and sort of the things going in the forward, our field is in an exciting phase. And sometimes or many times at lunch times or dinner or glass of wine, we complain we don't have enough money, and that's a fact. But if you sort of just take a look back from a rather high point of view, the field is both exciting as well as it turns out, very well funded. So the excitement has not gone unnoticed by, I would say, the funding agencies, because we are also entering the decade of mega projects. What used to be a mega project was rather rare, once every 20 or 30 years. We are now doing a whole bunch in maybe 10 years or 15 years. So if you look at ALMA, it's the world's largest astronomical, I don't know about largest, it's the most expensive astronomical facility. It's over $1 billion or €1 billion, it doesn't matter at that level. It's a very large number. And James Webb Space Telescope, it's now burning $1 million a day. So it's an easy number to compute. If you want to know how much is the cost, all you have to know is when it started, and you integrate, multiply by 1 million, and that's the cost. There are huge plans in Europe, big plans in Europe, in the US for extremely large telescopes at optical near-infrared. Their starting price is $1 billion or €1 billion, depending on which version you want. Laser Interferometer Gravitational Wave Observatory, LIGO in the US, Virgo, LCGT in Japan. If you add up the sum total investment in this field, it actually exceeds $1 billion now. In the US, LSST, which is the favored large project for this decade, has an initial price tag of $500 million. It doesn't include many things, and I'm willing to bet by the time it's done, even the run-out cost will be much more than that, into the next decade, you have LISA, which looks very exciting, at least a few billion. Square kilometer array, radio astronomers don't know how much it will cost. Everyone says it's $1 billion, but I don't think anyone understands the costing of this at all, so another few billion. Okay, well, this is all exciting. These are large projects. They'll do good things. And I'm not against that at all, actually, in case you may have sensed something otherwise. However, I think we should be a little careful. It's whenever excesses become very large, historically, I don't mean just in astronomy, the laboratory provided by astronomers in the social context is very small. But in the context of financial markets, whenever you have these sorts of large excesses happening one after another, it's usually a signal for disaster, actually. And it might be that this would be something that we have to watch out. We make fun of the physicists and SSC syndrome. We may be, in my opinion, close to it, actually. Okay, so that's just my personal view, because I don't think the world can actually sustain this sort of investment of money by any stretch of imagination. If you compare to other fields, this is a very large investment. Okay, so so I have two jobs. During daytime, I am involved in these large projects. So the director of Caltech Optical Observatories. I run Palomar. We're co-owners of Keck, and we are big investors for the 30-meter telescope. But my night job is much more interesting for me personally. And the night job is something that I would like to talk to you today. And it's what I call as a sideways revolution. I think there are opportunities here that go away from billion-dollar missions to actually do something very interesting. And the reason is that unlike physics, our subject is a phenomenological subject. Physics consists of the art of reducing observations and theory into as smaller numbers and hypotheses. Astronomy is all about discovery, make no mistake at all. The entry of physicists in astronomy, in my opinion, has clouded certain aspects of astronomy. Ultimately, astronomy is all discovery. Occasionally, we go and do physics, but that shouldn't distract us from our main goal. Okay, so I think unlike SSC and unlike the large projects I mentioned before, if you are willing, if you're creative, and if you have the license, the ability to do interesting things, there are many opportunities in this decade. And I'd like to show you the Palomar Transient Factory as an exemplar of what my hypothesis. Okay, so here's the Palomar Observatory. The funding for the observatory for the 200-inch telescope came a week before the great crash of 1929. Fortunately, Caltech had then a policy which was as soon as someone gave money, a check or a stock, you simply sold it the same day. Okay, so a week later, Caltech found itself actually having $6 million in cash. And, but there were a lot of technical difficulties in building this. World War II affected the progress tremendously. And finally, it was by about 1949, first light was achieved on the 200-inch. But between 1929 and 49, in those 20 years, Zwicky, who was the first astrophysicist appointed at Caltech, he had come to appreciate the importance of wide field imaging. Zwicky was a discovery power, absolute first-rate physicist, first-rate astronomer, but more than anything else, he was a great discoverer. So he had heard of the invention of the Schmidt telescope, so he came to Germany. He was funded by his wife's family to build the first astronomical Schmidt telescope. So that is the first one ever applied for astronomy. He in fact got the corrector lens from Bernhard Schmidt, the optician, and started a survey with the 18-inch Schmidt telescope. And it is this Schmidt telescope which led to the distinction between novae and supernovae, the various subclassification of supernovae, which we all take for granted, the 1 and 2s and the photometric light curves and all that sort of stuff. Along the way, he discovered, by the way, clusters of galaxies, evidence of dark matter, and even had ideas of lensing. And the 18-inch was so successful that Caltech funded him to build the 48-inch Schmidt telescope, which also came into existence about the same time as the 200-inch. And the idea was you'd survey the sky with this, if interesting objects would be studied with the 200-inch. And so the main work that was done by the 48-inch was the Palomar Sky Survey, which we, those who are young students won't know, but people actually took photographic plates and developed them. They didn't actually come on fixed tapes in those days. So POS 1 and POS 2 was done. It took a very long time to do those surveys, but it served as a fundamental catalog for optical astronomy. So here's this observatory, which is almost more than 60 years old at this point. So you'd say, okay, all these things like ALMA or JWST are happening, you know, so is it time to give up this sort of toy things and actually get on to some serious projects? I should also add, here's a 60-inch telescope for which was built for student training, in the sense the idea was that the students would do pre-thesis observations, monkey around, find something, and then eventually, once they have a clear idea, they use the 200-inch. Okay, so this sort of, so I think there are two different ideas in astronomy. Honestly, I think at this point, there's a more physicsy idea that you should do very big things, because that's where the actual action lies. And I think the CMB field is particularly, I think, particularly obsessed with doing very big things for the smallest possible numbers. So when you look at an old thing like this, you say, okay, what can we do? Well, I think we can do something very interesting if your idea is exploration. So here's what we have done with the Palomar Transient Factory is that we have constructed what I consider as the multiplication of the effort. That is, if you just take a 2-meter telescope, it's very difficult. I agree with it. You know, a simple 2-meter telescope at a reasonable site, you can be extraordinarily clever. I think it's difficult to make big discoveries. I agree with that. However, it's what I call as multiplication. So if you have a series of telescopes and you decide, okay, we will focus on a few things, then I think you can do something very interesting. To me, a prime example of this is something like Ogle, actually. But let's see, what we have done here is we have taken the 48-inch Schmidt telescope and equipped with a mosaic CCD, and this generates the discovery. So this is how we discover things. And then we can photometric follow up, and if it looks very interesting, we can do spectroscopy. Of course, you realize that there are two things convenient here. One is it's all on the same side. So if the night is good, it's good for all 3 telescopes. But I think the far more important thing is it's all run by the same person or same organization. That's far more important, and therefore, I'm not sure this is necessarily translatable in the European context. Okay, so I'll now describe a bit of what this project is doing. Project is about now 20 months old, and we have just last week submitted the 20th paper, so our publication is 1 a month, but I think this is actually slow. We should be more like 1 a week, given the abundance of data that we have. I will first motivate what got us into this project, which is mainly transients in the nearby universe, explain a bit of the actual nuts and bolts, how this factory is organized, and just give you a sprinkling of the results, because they're really all over the place. There is no theme other than lots of discovery and statistics. And maybe I have a couple of slides on the future. Okay, when I say transients in the local universe, I am specific here. Gamma ray bursts are transients, and there's a huge interest in finding gamma ray bursts at high redshift, which is an obvious and highly desirable goal. But I claim that there's a completely different reason why you want to study transients in the local universe, by which I mean approximately, let's say, 100 megaparsecs. Okay? It sounds strange because in astronomy, the more distant it is, the more excited we are supposed to be. But there are several fields in astronomy where, in fact, the rest of the universe actually doesn't matter. And you would say, well, that is very surprising. I never thought of this thing before. Okay, here are the fields. Ultra-high energy cosmic rays, okay? So we now know the existence of 10 to the 21 electron volt cosmic rays, okay? And we don't understand the origin. There are many papers, which is not the same thing as understanding their origin. And they have a natural horizon from basic physics. So here you are, let me assume for a moment you're a proton of with 10 to the 21 electron volts. That means your Lorentz factor is 10 to the 12, okay? And you're hurtling down towards you, the observer. And what do I see at the proton? I see 400 CMB photons per cubic centimeter, which are milli-electron volts. But now they're Doppler shifted, Doppler boosted, I mean, into my frame. And they're now into hundreds of MeV at this point. And therefore, not only I don't get the simple inverse Compton scattering, which itself is lossy, but in fact, the photon, CMB photon that scatters off me is so energetic it can produce pions at this point. So this cosmic ray, in fact, would slow down just by the scattering, the production of pions as it's hurtled towards you. So what is the scale of this? It's about 100 megaparsecs. It depends, of course, on the exact energy, but for this subject, the rest of the universe doesn't matter. They'll never see that stuff directly. Okay, what's the next one? High energy neutrino astronomy, very similar thing. We don't know if they exist, but it's not unreasonable. You have high energy leptons, high energy protons, so it doesn't take much imagination and basic physical thinking to, in fact, speculate there should be high energy neutrinos. TeV sources, okay. Just like where I described what I call as the GZK cutoff, if I have a very high energy photon and it's coming towards you, there are many backgrounds, not just the CMB, which is the low energy background. You could have the infrared background, you can have optical background, and you can have, as long as E1 times E2 exceeds MEC square, you will get production of pairs. So a high energy photon, in fact, has again an optical depth, which is highly energy dependent, and you ask, what is the radius of interest? Somewhere between 50 and 150 megaparsecs. For this subject, the rest of the universe doesn't matter. But perhaps the most interesting one in a certain sense, because it's really an entirely new window, is gravitational wave astronomy in the 100 hertz band. So this is the domain of ground-based interferometers, LIGO, Virgo, LCGT, maybe even IGO in the future. In this band, for which, as I said, if you add up, this is a major investment, and normally as astronomers, we don't pay attention, in fact, to most of these bands because they're kind of weird things out there. And whenever they only have 2 or 3 sources, astronomers don't care. But actually, these sources, these fields are now getting to the point where this is now, I would say, a fairly respectable field of astronomy. This one, as soon as we find a few sources, this one has now become mainstream, and this is awaiting discoveries. So for LIGO, unlike the previous fields I described, there is no optical depth effect. It's simply a one of sensitivity. Ground-based interferometers do not have the ability to see beyond, I would say, at the current time, 100 to maybe 200 megaparsecs. Okay. And therefore, in this field, again, the rest of the universe doesn't matter until you get into the LISA thing. One thing that's common to all these fields is their localization is poor, actually. And in particular with LIGO, 10 square degree localization would be an achievement. However, in 10 square degrees, we not only have the moon, we have the rest of the universe. So it's by astronomical standards, it's not enough to firmly localize, which galaxy it came and do all the usual astronomical things. Our coalescence is predominantly in spiral galaxies, is there an old component, all sorts of fun things that we like to do. And that's why electromagnetic, routine electromagnetic, by which I mean low energy observations, radio, optical, are very important. So for the development of this field, you really need to understand the transients, because these are all explosive phenomena in the volume. And that is the main purpose of the Palomar Transient Factory. And finally, a fun little thing in, ever since Zwicky's pioneering work of the distinction between novae and supernovae was made, it was noticed that there's been a huge gap if you plot the absolute peak magnitude of transients versus characteristic time scale, which usually is the decay time scale, and I show only novae here and supernovae of the type 1a, okay? And I do not show the type 2s with their envelopes because the envelopes mediate the shock and hide the actual explosion. So in that sense, 1a are the simplest naked explosion, so they are kind of easy to, their physics is actually very easy to understand. It's just the origin is difficult. Okay, so, so surely when you look at a figure like this, an astronomer would immediately say, what should I be doing to go and discover the rest of the phase space? And incidentally, a physicist, if he or she is any good, will immediately say there are two conserved quantities in this diagram, which is why you have two families. Okay, and that's why in general my observation is that physicists never make great discoveries. In astronomy, I mean. They are very bright people, but they don't have the sense of exploration. Okay, so as an astronomer, you know, you should say, what can I do to go and discover these wild zoos? So astronomy is like ecology. The universe is like an ecological system. There are all sorts of animals in this ecology. What we don't know is the occupation index of these creatures, and our job is to go and measure them. And there is no fundamental calculation you can do, okay, to compute this occupation index. And I must say something here. Last week I gave the Eddington lecture at Cambridge, and Eddington, a terribly bright astronomer, we will all agree on that account. But in his book, he says that he firmly believed that if you really thought through, and even if you had clouds all the time, you could figure the universe. I think history showed he was wrong. I think this is my point of why astronomy, these calculations are not fundamentally computable from first principles. You need actual observations. Okay, so here's Zwicky. I would say he's my absolute hero in astronomy in many, many ways. He was a great theoretical physicist. He contributed to the development of jet engines in the war effort. He had a great philosopher of certain ideas of looking at science. Great observer. He did his own measurements. It's almost impossible to think any parallel to any other astronomer from Pasadena. I think all of the astronomers from Pasadena would be 10 times or less impressive as Zwicky, in my opinion. And that is the 18-inch telescope that which we have now taken to a museum. Okay, so I started thinking about this problem about 2005 because I was working in gamma ray bursts, and I have a habit that when a subject reaches maturity, then I don't like to be in that, because then you have to really think and work hard because others are thinking and working hard. So it's much better to go and do something else. So I was thinking what to do next, and then I sort of developed this idea of why the transients and nearby universe are interesting. And so I knew that this is a good field because I don't know, there's an American term, sharpshooter, and I consider myself to be an astronomical sharpshooter, which means you take bets by having some knowledge, inside knowledge usually. Every day I would watch the supernova candidates that used to be announced, and this particular one from Kate, the Berkeley effort, they said, well, this is not a supernova because M85 is Messier 85, it's a lenticular in the Virgo cluster, and they said it's too faint to be a valid supernova candidate. Well, right away I knew this is my nova and supernova in between thing. We mounted a huge campaign, and it turns out to be one of these so-called luminous red novae, which we now know a few percent of the 1A rate are these objects called luminous red novae, lack of any better word, and we have no idea what their origin is. It's in fact a great field to be in because the number of luminous novae is in fact smaller than the number of theoretical models proposed. Okay, that's exactly the field you always want to be in. Okay, so to me it's somewhat astonishing when I see our cosmological friends where the number of model is 1 and the number of papers is 10,000. Okay, well, sorry, it's nice to sometimes make fun of popular fields. Okay, so let me go back to my phase space, and you can see already the little beasts are coming up. Here's a little group now of luminous red novae from the year 2005. There are other things coming up here, and there's something which you don't understand at all. But I want to focus on this particular box, which I call as the gap. because I think the electromagnetic localization of gravitational waves, in my opinion, is a very important goal. Because I know what the first paper, LIGO and Virgo people will write. We saw a chirp signal, okay, fine. I want to know what's the second paper they'll write. Okay, they can say we saw a chirp signal again. Okay, that's fine, but I really want to know what is the second important paper. Second paper has to be we saw a signal, we localized, and here's the galaxy it came about. Okay, and I want to be on that. And for that, I think you have to be in this. So I don't have time to get into, but on rather general considerations, you can show that if you have coalescence of two neutron stars, or even a neutron star and a black hole, there'll be some amount of debris that actually will escape to infinity, and the optical depth for any reasonable value of this debris will be high enough that this event will last hours, perhaps even a day. Okay, so here's a picture, not a picture, here's a real high quality model from Rupert and Bianca, and it shows a black hole. And the simulations start off where the neutron star is about to be tidally disrupted, and most of the neutron star will rain down on the black hole. We believe that, in fact, when it rains down, jets are formed, and this is a very popular model for short hard bursts. But what we are interested is some of the material here that will, in fact, escape, because recall that in a neutron star, the neutrons do not undergo decay because the Fermi energy is very large. So that makes it, unlike a neutron in this room, it will decay in 10 minutes, but because there is no Fermi energy in this room that's worth anything. But so as soon as this Fermi energy is released due to the disruption of the neutron star, it's very easy to see that you will form a very complex radioactive chain, and even just the decay of a neutron is enough to power the mini supernova, a model first noted by Lee and Paczynski. So it is this mini supernova that, if you then say what is the optical depth, because you want to know how long it lasts, you can argue on rather general terms this will be of the order of hours to a day. Okay, and that's what we want to go and look at. Okay, so the way it works, I don't know how it works in Europe. I suspect probably not too dissimilar in the US. If you want to get funding, you can't write a proposal that says, I've been doing this business, trust me, give me money, I'll go make discoveries. It generally doesn't work. And you have to show you're a very great scholar. You have to throw in, it helps to have a few theoretical underpinnings, a few equations, diagrams. Those are all necessary. So every proposal I write, I have to always figure out what is a winning diagram, so it all looks very scholarly. And this is the scholarly thing I threw in, and it did win. It has all the trappings of a scholarly thing. It's got all the possible discoveries one can make. You can then appeal to each of these. You can put in about 5 references. Hopefully one of them will be the referee, and soon you're winning some friends and supporters. Anyway, so this is our standard going in phase space picture. And you can see, apart from the somewhat mild cynicism I exhibited, that this phase space, in fact, can be populated by plausible physical models. Okay, so now let me I hope I motivated you into, or convinced you that the nearest 100 megaparsecs is in fact the most exciting volume that all of you should be studying. And so I'll tell you how we go about doing this now with the transient factory. So the basic idea, which gives PTF right now the largest discovery rate compared to PanSTARRS or SkyMapper, is that it's a highly focused project. So let me explain why the sort of the synergism of 2 telescopes gives you a very large discovery reach. So let's say if you want to do a wide field survey, like SkyMapper or PanSTARRS, they have multiple goals. One goal is to make an image of the sky in many bands, which is a basic astronomical goal, to catalog the sky at a given time in bands, so you can then do lots of studies, a very worthwhile goal. However, from a point of view of transients, that's a wasted effort, because if I take a picture with this 48-inch Schmidt telescope, and right now the CCD has a field of view of 10 square degrees. If I take a picture for 60 seconds, I achieve 21st magnitude, and ask what is the fraction, how many transients will I discover? When I say transient, I mean something that rose from the sky, we didn't have anything in quiescence, and rose and is detected, the answer is 0.1. So I have to take 10 frames to get a genuine transient. So from my point of view, or the point of view of transients, each picture is about 100 megapixels, so I have to take a gigapixel of data, and then I'm interested in only few pixels of that sort. Okay, so when you do large projects like SkyMap or Pan-STARRS, you are using all that data, but here we don't care. So what we do is we analyze the data, we find the transient, and then transfer that to the detailed study. So instead of trying to do all the band observations for all the pixels in the sky, we only do the multi-band observations for only transients. Of course, that's a definite trade-off. But as a result, the reach or the ability for PTF to discover is much larger than this project. So our current discovery rate on a good night, if the machine is all tuned up, we can discover a supernova almost every 20 minutes. And a strong transient, by which I mean more than 10, or strong variable, by which I mean more than 10% flux, or delta M of 0.1 is every 10 minutes. Okay, so on a good night, you can just go and find supernovae literally by the dozens. Okay. Okay, and those which we find interesting, we do multi-band observations. This is a highly automated system. There is no operator. Each one of them doing this work was a thesis project where students who work with me, I really like them to do some things with their hands, because I think pure observers I never find very interesting. So students learn how to talk with the engineers, automate things, and at the very least, they have employment opportunities that are vastly expanded beyond astronomy at this point. Okay, so a large number of young people. This is a project on the cheap. The total cost, capital plus ops cost for 5 years, is $2.5 million. Okay. And the people, each of these young people have definite responsibilities, and these are the institutions. You see Berkeley, IPAC, Lawrence Berkeley Lab, Columbia University, Oxford, LCOGT in Santa Barbara, and Weizmann Institute in Israel. Okay, this is the old CFH-12K camera. So I don't know if anyone is associated with this, but Christian Vier at Hawaii was very kind enough. It's a hand-me-down. For a very modest amount of money, they sold us the CFH-12K, which speeded the project. One of the high-road devices is dead, so we didn't bother replacing it. And this is about 8 square degrees, the customary moon, to show you the scale of this project, the angular scale. Okay, one of the things in our design specs, we had to re-engineer the CFH-12K with cryo coolers and jukeboxes, the usual sort of things that go on in this, which I won't won't go in details. But we had only put a engineering science spec of 1% as 1 sigma, because the idea is to do transients, and why bother going something? Because if you go if you go to more and more variable sources, almost every source in the sky is variable, so you then get inundated. However, it turned out that the RMS, the stability of the system is incredible. We're actually reaching photometric stability of a few millimagnitudes, or the range of from 16th to about 10th, at which point it saturates. And that has completely opened up a new area which we had never anticipated, and that is to search for transits by field M dwarfs by their planets. And that has now become a large project. And of course, I think we have about 100 eclipsing M dwarfs. We may even have an M dwarf and a brown dwarf. So I think this project is actually on the verge of making something interesting. As you can see, an M dwarf transiting by Jupiter is an incredibly strong signal here. The advantage of such discoveries compared to other projects, like certainly Kepler, Corot, is that these will all be nearby objects. Okay, so there's lots of fun things you can do. Okay, so I have to tell you something about, before I go into the software details. I remember a long time ago when the Sloan Digital Sky Survey, which in my mind is one of the most successful projects in the last 2 decades in astronomy, was being planned. I thought the number I remember was the total cost was supposed to be $18 million. Now, of course, the project got the numbers right. They were just somewhat, the order was wrong. I think the total cost in the end was $81 million. And you say, what happened? How did 18 become 81? And that's because astronomers, I think we learned a valuable lesson from Sloan. And the lesson is that many of these projects are actually dominated by software. I think the old plans since Sloan must have been, oh, well, over the weekend I'll use Fortran 1 or Fortran 2 or whatever people use those days and write little programs. But software really completely dominates the cost of these projects. Okay. And therefore, for PTF, the way it's set up is that I find software is so hard and is so invaluable that you never pay for software. You should always have agreements with people to write software. So the software is, in fact, the hardest part. And fortunately for us, Peter Nugent, who's, I think, one of the world's great expert in image subtraction, he is in charge of image subtraction. He has the resources of the Department of Energy's supercomputer system and 20 years of knowledge of the art of image subtraction. So if you do an image subtraction, even with all the niceties that that people have learned over many years now, there are a lot of artifacts, okay? And many of those you can eliminate. It will turn out in a typical night, if you didn't do anything, if you just say anything about 3 sigma, you'll get a million such things. You can now eliminate them, hot pixels, bad columns, imperfect subtractions that are easily statistically recognized. But in the end, you'll have in a night maybe about 1,000 things which require closer inspection. Okay, and so the solution for a while in the beginning was that we used to look about 4 or 5 of us would look in the afternoon at these candidates that were filtered out by the machine stuff, and it took about an hour, 6 man-hours to do this. And it turns out we can train a person for about 15 minutes and they'll become very good at saying, okay, this is really a proper source and this one is in fact an artifact, rather subtle artifact. And it got tiring, and our colleagues at Oxford came up, they had finished this Galaxy Zoo project, and so they developed very rapidly a supernova zoo under the Galaxy Zoo framework, and it was fantastic because there are these thousands of people, and we simply send a note saying we have some observing run, please help. And I just don't really understand it, comprehend fully, but within a few hours, we'd actually have all this sorted out by all these volunteers. And I can tell you, with the empirical data, a good astronomer here we know by the truth. If someone has said this is a genuine transient, because we usually go observe, we in fact know whether it's a transient or not. So in fact, we know after the fact whether it's true or false. I can tell you the average of 10 responses from the supernova zoo is as good as a trained astronomer, which is a bit of a letdown to think that any of us is only 10 average people in the streets of Paris could just do as good a classification as any one of us. Okay, but anyway, that has been great. But really the next step is in fact to use this sort of what humans recognize and into making it into a machine sortable thing. And we're almost there. Josh Bloom at Berkeley, he's with his group with statisticians has almost perfected this what humans do in recognizing and vetting the candidates. Okay, so image subtraction is something you want to do, I won't say in real time. Nothing we are trying to do is on minutes time scales, even though that's not we are not out at that speed. But the next one really is to have finally reduced archive quality photometered, astrometered images, and then of course the source extraction. And that's done by Jason Suresh out of IPAC. And we're already creating one of the largest databases because roughly in a year we visit most of the northern sky about 30 times. And the sources get repeatedly detected. Okay, so there are a large number of key projects. This is run in a rather in a fixed way. What we have is about a third of the time goes into the bread and butter, which is to optimize to find supernovae. So by which I mean supernovae are things which rise to peak about 2 weeks and take another few weeks to decay. So a 3 or a 5 day cadence is good enough to find supernovae. Okay? But 1/3 is reserved for whatever else. Okay? So this is the advantage of being a PI project is we say, okay, next 4 months, why don't we go and mess around and look for things that change in the middle of the night? So you look at the same field 2 or 3 times, it looks interesting, then we continue that. If not, we go on. So which we call as the short cadence. And then there are some rather specific projects. One is on Orion. So for a month, we observe Orion. Orion rises. We take data every 30 seconds. Orion sets, we stop, and we do it for a month. And we are now more or less finished the rotational history of Orion and several other open clusters. It's a really beautiful sort of stellar astronomy. The planet search is, as I said, a new thing that has come up. And then there are a few other things. So sometimes we respond to large areas, for example, an ice cube or LIGO or GLAST, GBM, so TO things where the localization is not very well known. And we are planning to start an H-alpha survey, which during the full moon. Okay, so the PTF haul to date, it's already a month out of date. I think we've crossed 1100. When I say supernova discovery, I don't mean we found something which looks like a supernova, because it's next to a galaxy. I meant we actually have spectra, and we can tell you what it is and details. We already finished 1100, which I think is the largest of any such homogeneous data product. And here's the distribution into a variety of things. And the 1A project is certainly contributing a lot to the study of redshift 0 1As, which I'll talk a bit. The type 2s, we are doing statistical studies. These are we have an active program trying to understand the connection between these and GRBs. But the most fun part is, of course, the 3% that we don't know what's going on. Okay, so some results. If you go to our PTF webpage, I don't want to go into this, but we have all the way from supernovae to stellar astronomy to protostars, and this is already a couple of papers behind. Okay, so let's first talk about shock breakout. Okay, so consider a star, and it has an explosion in the center. We don't care why the explosion happens. Is it maybe thermo-nuclear ignited, formation of a compact object? It doesn't matter. So a very strong blast wave that's propagating inside the star. Okay, the blast wave is so strong that, in fact, the post-shock gas is very hot. And because it's so hot, you generate photons. So the photon pressure alone, but the photons can't escape because the optical depth is large, so they're trapped inside. So you have this mixture of photon and matter bubble that's expanding. But when this shock wave reaches close to the surface, for the first time, the photons can escape, okay, and that's called shock breakout. And it's a very brief pulse. And then the blast wave essentially leaves the star. There's most of the energy of the blast of the explosion is now inside the star, and eventually the star expands. It interacts with the circumstellar matter, or if there isn't any, it just cools down, and if there is radioactivity, it gets heated up. So those are the supernova phase. So there's a very brief period when the first photons leak out, the shock breakout. If you can measure the duration and the magnitude or the flux of that, you actually can say something about the size of the stars, the size of the progenitor, which is a very important clue. Okay, so for very compact objects, this will be short. The signal will be in the X-rays. But for extended objects, red supergiants, blue supergiants, we have a chance of seeing this with PTF. So one of the things that, so we have seen some by themselves. We have several 2Ps where, in fact, we see a rise and then a decay and then the eventual supernova rise. But the one that's been most fun, in fact, that I would say has been unanticipated and at least, but in retrospect, understandable, is something we found in concert with Galax. Our sky mapping rate is so large that it's by sheer accident we actually observe the fields that Galax has observed. And one of them was very interesting, PTF09UJ. So here's the Galax observation, and here are the various PTF observations. What we found is a very, very strong ultraviolet signal, which didn't make sense at all from a routine shock breakout. And then the explanation is that what happens is that these very massive stars, the picture I gave you of a shock breakout is incomplete because the picture I gave you is star with a finite, with a clear edge, explosion inside, and a vacuum. But very massive stars are not that. They, in fact, lose a lot of matter, as you know. In fact, a huge fraction of the matter is lost through strong winds. The circumstellar medium is very rich. So what happens is that the shock breakout photons come out, but the circumstellar matter itself is optically thick. So they don't leak out. So the shock breakout is reborn again. And what we saw was the shock breakout reborn again at much larger radius, which explains both the long duration as well as the brilliance of that. And so this is an entirely new way to look actually to study the circumstellar matter, which until recently the radio observations were very good at doing this. But we have a very different approach of doing shock breakout or the reborn shock breakout. Okay, one of the things we can do when you have hundreds of supernovae is you can do statistics. Now, as you know, there's been suspicion that the IMF in fact is not a universal number. It's not a fixed law, okay? There have in fact been even suspicions that IMF varies from locale to locale, so that it be something like in dwarf galaxies, there's an idea that they're low metallicity, maybe their GMCs are different, they will form more top-heavy objects as compared to giant galaxies. Well, the easy way to settle is to look at the supernovae, and because the 1BCs are in fact supernovae that are the most stripped ones. Likely they come from the most massive stars, okay, because they have undergone the largest. So if we compare between giant hosts and dwarf galaxies, our first study already shows some systematic differences, which I don't want to go in detail, but it's roughly in accord with our prejudice that the most massive, that the giant, small galaxies, dwarf galaxies, in fact produce more massive stars, or at least of the sort that eventually lead to 1C explosions. Okay, so let's go on to supernovae of the type 1A. As you know, this is a major, perhaps the biggest subject in astronomy now, is the fact that if you look at 1A supernovae and you standardize them in the way the Phillips relation does that, and you compare the local sample to, let's say, redshift 0.7 or 1, then they're dimmer than what you expect, and that's because there has been expansion of the universe. However, there's a problem. You're comparing these local objects, redshift 0, in the same band as over here, because the optical band is very sensitive right now for observations. So you're comparing basically optical here to the optical there, but the optical for the high redshift ones is really rest frame ultraviolet. So there's always some concern that are you comparing the apples to oranges, that in fact you may have, that this may be a cause for concern. And so the right way to do, or one way to do, is in fact to do these in optical, because that's still very sensitive, but to do these in ultraviolet, okay? Then we'd be doing like to like. We'd sort out this, we'd take away this fundamental uncertainty. Well, there's one problem, that to do ultraviolet observations, you need to go to space, and the Hubble Space Telescope has a very nice spectrometer, but it requires all sorts of notice to organize this. So every Thursday, the schedule for Hubble is loaded. So at that point, if you can have supernovae, which you guarantee would peak by the time they start observing, with the UV, you'd be set. So what you need to do is find supernovae 2 weeks before they peak. And we are at the capability where we can, in fact, do that quite easily. So this is an early diagram. So this shows, in fact, a redshift of objects we find versus their magnitude. If you find supernovae at peak, then they'd be on this line. But 2 weeks before that, they'd be here. And you can see, in fact, we are now finding things beyond 2 weeks. So typically every Monday and Tuesday, when we had this program, Nugent, Ellis, Howell, and Sullivan, and others, we do an extra bit effort. We'd say, let's fish out those 1As, and then by Thursday, we'd load them up. So this group now has about 36 or 50, I don't know, 1A UV spectra. And being somewhat mischievous, you know, even though I'm an atheist, I would every day pray to God, you know, hopefully the dark energy signal will disappear and disappoint my friends. But unfortunately, I have to tell you that all the UV spectra, in fact, show there is nothing amiss at all. The comparison of UV with the 0.7 redshift optical turns out to be all okay. Here's some initial pictures, and they even published this paper. Okay, then I remarked that 3%, so of the order of 30, which are peculiar in one way or the other way. So here's 2005 E, rather famous supernova, remarkable for being a type 1 supernova, but in the halo, and there are lots of ideas of what it could be, including the coalescence of white dwarfs, which is a model I particularly like. We have a whole bunch of them now. Okay, in fact, and we are now undertaking a big study. Their nebular phases seem to be dominated by calcium. So hopefully we'll be able to sort out the origin, because it's not unreasonable, without even worrying with the origin of 1A. We know there are double degenerates in the sky. We even know some of them have coalescence duration less than the Hubble time. So they will coalesce. Question is, what will they make? And I think we are getting now data to actually start playing around with these ideas. Here's a particular one, PTF10 BHP. It's remarkable for its incredibly short rise time and a decay time with an exponential decay of about 4 days. Now, some of you may immediately recall that even the nickel timescale is not 4 days, 5 days. So we know it is quite different. And so this is an explosion. The short rise time really requires a very small amount of ejecta. And the short decay, the decay timescale being somewhat less than nickel is consistent with the idea that the ejecta is so small that the gamma rays that are produced on decay of nickel, in fact, do not thermalize. They, in fact, escape after only 1 or 2 scatterings, which would then explain why the bolometric luminosity would be less than that. So this is a supernova with a total eject of 0.1 solar masses and a nickel production maybe of about 0.03, and quite consistent with the idea of coalescence of white dwarfs. Okay, then I talked initially about luminous red novae. This is, as I said, has now become main business. In fact, so this is a PTF10 FQS in, I think, Messier 99 is a Hubble picture. These are amazing. These are the most dominant mid-infrared transients. These transients, they start off in the optical for a week, but they very systematically march across. If you do a new F-nu, the peak slowly marches across. A year later, you can see it in Spitzer bands. So we got intrigued, and in fact, as you know, the WISE Observatory, which does its mid-infrared mission, it was able to map the sky 1.3 or 1.4 times. That is, it mapped the sky fully and then did a second pass for about a third of the sky. So we started looking at the differences, and in fact, these are the longest lived mid-infrared transients, and a paper will soon be published. Okay, the next one is luminous supernovae. A few years ago, a supernovae called 2006 GY became famous because it was, I forget, 10 or 20 times brighter than a typical 1A. But I'm not talking of these supernovae which are massive. They have very rich interstellar medium. Therefore, when the shock wave goes off, you really can convert the mechanical energy into radiation at a very high rate. I'm talking of genuinely a new class of supernovae, and this is a project led by Robert Quimby, who will soon be heading to IPMU in Japan. So here's the usual picture, before, after, or before and the discovery. And so Robert started noticing that these supernovae, which are very blue, let me characterize, and they live for a long, long time. So you can see that the time scale here is in days, in tens of days to 100 days. Okay, and these are. And in particular, there's a supernova called SCP-06F6, very famous, at least in our little field of supernovae. Until a year ago, if you went to a meeting, it's everyone, the standard supernova in a meeting, people say, oh, what is SCP-06F6? This was discovered by accident by Barbary et al. With the Hubble Space Telescope when they're looking for supernovae in clusters. And that's plotted here because it turns out they're all related. So let me tell you what these are. We call these as luminous supernovae of the type 1C, okay? Because there are luminous supernovae of the type 2N, which are actually somewhat well known. The characteristics are they're 10 times brighter than supernovae of type 1A. So about minus 22nd magnitude is a typical number. They show no hydrogen. We can't say anything about helium because in order to see helium, it has to be very hot. So we don't know. The duration is long, 100 days. The plateau lasts for about 100 days. Very strong UV emission, which unlike, for example, 1As, which have a very strong resonance lines from metals. These things, in fact, have a new to the 1 spectra that goes all the way into the ultraviolet. I'll show you a typical spectra. And the inferred progenitor radius is very large, 100 AU. Okay. So think of this. There's a star. It has no hydrogen. It's perhaps even dominated by CNO. Maybe it has helium. I don't know. And yet its starting point is 100 AU. And its total bulk radiation is 10 to the 52 ergs, 10 beta. Okay. And the peak luminosity is very large. Okay. So of course we can immediately, if any good astronomer can write 3 different models already with this data, and 3 such papers have already been written, but let's not go there. So let's look at the data. And the reason it took a while for Robert to recognize this as a class is that here's SCP-06F6. And this is a great object because 1 discovery and 8 model papers came out within the same, and all the model papers are wrong anyway right now. He was able to show by a sequence of these PTF observations that in fact that these peculiar undulations that we're seeing are in fact rarely seen due to oxygen 2. This is a so-called synophyte. And in fact, we now have a sequence of these supernovae, and SCP-06F6, in fact, is the most extreme example or the most distant member of the supernovae of the luminous supernova of the type 1c, a redshift of 1.2. So why is this exciting? Here's a swift observation of one of these candidates. And you can see when you stitch the optical with the UV, it screams away into the UV. So these are bright objects. They live a long time. They're bright in UV, which means they have positive K correction. You can do all sorts of fun things. So the new avenues, I won't go into detail, but there are reasonable theoretical arguments why these are in fact the death throes of very massive stars. I would say until this discovery, the idea that such massive stars can happen at low redshift wouldn't have been so obvious. Okay, so one idea is maybe there are some pockets of the local universe which are forming stars almost the first time, maybe the second generation. So there are many ways to test that. They arise in tiny galaxies. Some of them look very metal poor. And I can't tell you the metallicity exactly now because the supernovae live for so long, we have to wait till they die before we can, or they disappear before we can even get the metallicity. But because they have such long-lived and they have UV bright, you can actually use them like GRB afterglows, except more convenient because they last a long time, to probe both the IGM as well as the ISM in the host galaxy. Okay. And of course, because they fade, you can do the usual trick. You can study DLAs along the path, before and after, and all this. The part I like the most is I really want to believe that, in fact, we are finding these would, in fact, be representative of the earliest generation of stars. And again, being somewhat mischievous, it will be nice to do this even before JWST happens because these are actually next door. Okay, so here's a movie which shows the epoch of observation, and that's telling you certain statistics. You know, for example, here it's saying by that date we have achieved 1500 square degrees greater than 25 epochs, and that many square degrees greater than 100, and that's the bar here, which tells you black means we have not observed. So that's telling you the sky coverage as a function of time. Okay, and so let me play that again because while our focus so far has been on, in some sense, the easiest part has been to do supernovae. You find things, you run around. The really fun stuff is somewhat harder because it really requires great software pipelines, which are still not working for us, is in fact to use the repeated looks on the sky to do all sorts of fun things. So for example, here's just a simple example. The ROSAT All-Sky Survey, only half the sources are identified. Okay, it's a venerable survey. So one of the things that we did just for fun is looked at an intermediate ROSAT source which has not been identified, and we just took that piece. The PSPC circle is about 30 arc seconds. So within the 30 arc seconds, we looked at all sources that PTF had observed in this particular field about 50 times. We found a violently variable source. We went and observed that, and it's an intermediate polar. Okay, so, but by the time our software is finished, we can very quickly, we can even write this great paper, 8,000 or whatever, 6,000 of 8,000 ROSAT sources identified in one paper. Probably will be a nice undergraduate thesis project. Okay, well, so these are the kinds of things you can really start doing once you have this sort of large database on your hand. So as an example of that, is something which, again, is not my field. Is we found a source, PTF10HJZ. Okay, it looked very intriguing. Here's a nearby galaxy 20 megaparsecs away, right apparently across that was the source, and it fluctuated a lot and all the usual stuff. Okay, so we eventually, for a while, we thought it is a short, hard burst and all this. Well, to make the story short, it is a blazar after a lot of hard work, and it is also a Fermi lat source. So actually, by the time we do this, we can. It's very difficult to identify the faint Fermi LAT sources because their error circles are large, 8 arc minutes. But the chance of finding a violently variable optical source and in an 8 arc minute is pretty low right away. So we can sort out all the faint end of the Fermi LAT sources through this. Here's one. I won't go into detail. It was a paper submitted last week where we argue it's, in fact, a tidal disruption flare in a very low luminosity galaxy. Okay, so let me end by saying we're thinking of some new initiatives. The first one is the hardest part is you've got to classify these things. So we're building inspired a bit by SNFs, but going the next step, a very low resolution IFU spectrograph, whose main goal is to classify. When I say classify, I mean get a low resolution spectrum just barely good enough to say, is it a 1A or not 1A? That's already very critical for us. Is it galactic, not galactic? And then we want to install this on 2-meter telescopes next to you and have an army of robotic telescopes. We discover, 2 minutes later it's characterized, and because that would be, I think, a very fun thing. Thinking of something called NGTF. It's always good to have your next First, I thought we should call it PTF2. But then my teenage daughter remarked, she said, if you've seen a movie called Rocky Horror Show, would you really go and see a movie called Rocky Horror Show 2? And I said, no, I guess not. So we'll call it as NGTF. That's a new thing. It's always next generation, right? So next generation transient factory, which is to, in fact, increase the field of view to the fully available Schmidt field and do either high cadence or very large surveys. And I won't go in detail, but I've been completely disenchanted with this large project. So I have a completely different idea, which I call less is more. So with a group of people in India, Israel, and Canada, we're designing a so-called less is more satellite, LIMSAT, which is, in fact, we have a satellite that will serve ground rather than the other way around. So let me end by showing you this picture that we are exploring here through a relatively modest project using existing equipment. The next generation, we can get into this domain, and who knows, maybe there won't be much, maybe there will be much, but that's our business, is to go and explore. Thanks very much.